Hello and welcome to the following revision session for AQA A-Level Physics on the topic of nuclear physics, in particular looking at the concept of nuclear processes. So in today's revision session, if we've been successful and we've learned today, we should be able to answer A-Level Physics examination style questions, assess your understanding on A-Level Physics, and finally understand what topics we need to work on to improve for A-Level Physics. So how do you prepare for this revision session? When you're completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. And in this left hand side section, write down your working out and answers to the questions in the revision session. When you're doing this, make sure to write in full sentences and show your full working out. Whilst in the right hand side, write down any bits of information which you find useful, any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you revise AQA A-Level Physics? Well, the first step is to learn the key facts. Use revision guides, class workbooks, prep notes and textbooks to learn the key ideas of the course. Then test yourself. Use Caboodle, Seneca and knowledge checkers to quickly test your own knowledge. Then practice exam style questions. Use exam preparation books, homework books, study books, workbooks to answer exam questions and to mark your own work. So the three steps are to learn the key facts, test yourself, and then practice exam style questions. So what are the key facts to do with nuclear physics? Well, the first one is mass energy equivalence. E equals mc squared, so energy and mass are interchangeable, and this applies to all forms of energy change in nuclear processes. Now, binding energy is the energy required to separate a nucleus into its constituent protons and neutrons. The mass defect is the difference between the mass of the nucleus and the sum of the individual masses of the protons and neutrons. 1U is 1.661 times 10 to the minus 27 kilograms, or 931.5 MeV. Now, the safety measures in nuclear power stations are shielding to reduce radiation exposure, remote handling of fuel rods, emergency shutdown systems to quickly stop the reaction, and the fuel is typically uranium or plutonium. Now, the radioactive waste management system is that waste is stored securely, often underground or in water pools. It must be monitored due to long half-lives and high activity. Now, the benefits of nuclear power stations are low CO2 emissions and a reliable baseload energy, but the risks include accidents and long-term waste and high storage, and then high cost. Now, induced fission is when fission is triggered by the absorption of a thermal neutron. It splits a heavy nucleus into two smaller nuclei, releasing energy, more neutrons, which may cause further fission, a chain reaction. Now, the critical mass is the minimum amount of fissile material needed to sustain a chain reaction. Now, the moderator slows down neutrons via elastic collisions to make them thermal neutrons. The material for this is either graphite or heavy water. The control rod absorbs excess neutrons to control the rate of reaction and is either boron or cadmium, whilst the coolant transfers heat from the reactor core to the turbines. Materials include water, liquid sodium and carbon dioxide. Now, you do need to understand the function of each component. Let's now have a look at some general questions to do with nuclear physics. So, what is meant by the mass defect in a nucleus? That is the difference between the mass of the separated nucleons and the mass of the bound nucleus. What is bind energy? It's the energy required to separate a nucleus into its individual protons and neutrons. What is the value of one atomic mass unit in MeV? 1U is 931.5 MeV. What does the graph of the average bind energy per nucleon against nucleon number show? It shows that nuclei with intermediate mass numbers like iron have the highest bind energy per nucleon and are therefore the most stable. Which region of the bind energy graph corresponds to nuclei likely to release energy by fission? It is the nuclei with large mass numbers. Which region of the graph indicates nuclei likely to release energy by a fusion? It is the nuclei with small mass numbers. How can bind energy calculations be used to find the energy released in a reaction? It is done by finding the difference in total bind energy before and after the reaction. What type of neutron is most effective at inducing fission in uranium-235? It is a thermal or slow-moving neutron. What is meant by a chain reaction in nuclear fission? This is a process where each fission event triggers neutrons that trigger further fission events. What is the term for the minimum amount of fissile material needed to sustain a chain reaction? It is the critical mass. What is the function of the moderator in a nuclear reactor? It is to slow down fast neutrons through elastic collisions so they can cause further fission. Which materials are commonly used as moderators? Graphite in heavy water. What is the function of control rods in a nuclear reactor? It is to absorb excess neutrons and to regulate the rate of fission reaction. Name two materials commonly used for control rods. Boron and cadmium. What is the role of the coolant in a nuclear reactor? It is to remove heat from the reactor core and transfer it to a heat exchanger or turbine system. Give one material commonly used as coolants in nuclear reactors. Either water, carbon dioxide or liquid sodium. Why are elastic collisions important in the moderation process? They allow neutrons to lose energy gradually without being absorbed, maintaining their ability to induce fission. Why must nuclear fuel be handled remotely? Because it's highly radioactive and therefore poses a health hazard to humans. What is the purpose of shielding in a nuclear power station? It's to absorb harmful radiation and protect the workers and the environment. Why is an emergency shutdown system essential in a nuclear reactor? It is to rapidly stop the chain reaction and prevent overheating or meltdown. What are some of the challenges in storing radioactive waste? It is that it remains dangerous for thousands of years and must be securely stored to avoid contamination. Let's now have a look at some questions regarding nuclear fission. The table below shows simplified nuclear data for hypothetical analysis comparing fusion and fission energy yields. Calculate the energy released per nucleon for each of the two nuclear reactions above. Which reaction releases more energy per nucleon? Show all working. Explain, using a binding energy per nucleon graph, why both fusion of light nuclei and fission of heavy nuclei release energy. You are not required to draw a graph in your answer. A nuclear policy advisor claims fission is clearly better than fusion because it releases more energy in total. Evaluate this statement using your previous calculations and further physics considerations including sustainability and practicality. So pause the video now and then unpause the video when you want to go through your answer. Right, we know that in the first question the fusion energy is going to be equal to the mass difference times by 931.5 because I'll get into MeV. So you get that to be 17.61 MeV. You divide that by the number of nucleons present, 5, so you get 3.52 MeV per nucleon. We do the same for fission and we get it out to be 0.74 MeV per nucleon. So therefore fusion releases more energy per nucleon. Now the binding energy per nucleon graph rises steeply for small a. So for fusion, light nuclei like hydrogen and helium move up the curve and release quite a lot of energy. For fission, heavy nuclei like uranium split into medium-sized nuclei which have a higher binding energy per nucleon. In both cases, the increase in binding energy per nucleon represents the energy released. Now fission will release more energy in total, but fusion is more efficient per nucleon. Now fission produces long-lived radioactive waste, but fusion does not. Fusion fuel, hydrogen isotopes, is more abundant and sustainable. However, fusion is currently technologically difficult, so practicality limits adoption. The table shows the atomic masses of selected nuclei in a fusion reactor. In a fusion reactor, a deuterium nucleus and a tritium nucleus combine to form a helium-4 nucleus and a neutron. Calculate the energy released in this fusion reaction in MeV. Explain how the graph of average binding energy per nucleon against nucleon number supports the conclusion that energy is released in this fusion reaction. A student claims that fusion always releases more energy than fission. Evaluate this claim using your understanding of nuclear binding energy and the conditions required for each process. So pause the video now and then unpause the video when you want to go through your answer. Right, in our first one, we work out the total mass before. So we add up the values of the deuterium and tritium and we get 5.030151 U. We find the total mass after by adding the helium and the neutron to get 5.011268 U. We find our mass difference by subtracting one from the other, so 0.018883 U. We then multiply by 931.5 to get into MeV, which is 17.6 MeV. Now, the binding energy per nucleon increases with fusion of like nuclei. Helium-4 has a higher binding energy per nucleon than deuterium or tritium. The increase in binding energy per nucleon means that energy is released. Now, the graph shows the fusion of like nuclei moves towards the peak of this curve. Finally, fusion of like nuclei releases large energy per nucleon due to the large increase in binding energy. The fission of heavy nuclei also releases energy, but from a different region of the curve. Now, fusion requires extreme conditions of high temperature and high pressure, so it's not always more practical or efficient than fission. The graph below shows the average binding energy per nucleon for a range of nuclei. The peak of the curve occurs near iron, with a binding energy per nucleon of approximately 8.8 MeV. A physicist proposes a hypothetical element X with a nucleon number of 60 and an average binding energy per nucleon of 7.5 MeV. Explain using energy considerations whether element X would be more likely to undergo fission or fusion to release energy. Justify your answer with reference to the binding energy curve. The physicists suggest that if element X could be split into two identical nuclei with a higher average binding energy per nucleon, the total mass of the products will be less than the original mass of X. Discuss this suggestion in terms of mass-energy equivalence and the implications for energy release. Evaluate the following statement. The most stable nuclei are those with the highest total binding energy. So use your understanding of nuclear stability and the binding energy per nucleon graph to support your answer. So, pause the video now, and then unpause the video when you want to go through your answer. In our first one, the binding energy per nucleon increases in fusion of light nuclei and the fission of heavy nuclei. Element X is near the middle of the curve. Now, since its binding energy per nucleon is lower than iron, increasing it would release energy. So therefore, fission is more likely if splitting increases the binding energy per nucleon. Now, if the products have a higher binding energy per nucleon, the total binding energy will increase. So this means that the mass of the products is less than the original mass. So the mass difference corresponds to the energy being released. Finally, the total binding energy increases with nucleon number, but it's not a measure of stability alone. The binding energy per nucleon is a better indicator of stability. The most stable nuclei are near the peak of the curve, with the highest binding energy per nucleon. So this statement is misleading. The higher total binding energy can mean less stability if the per nucleon value is low. The next question says, on a deep space station orbiting a gas giant, engineers are designing a power generator called the Kepler engine to sustain the outpost for 100 years. It uses nuclear reactors to generate energy, and engineers are debating whether to base the reactor on controlled fusion or microfission. To make their decision, they compare two test reactions. Calculate the energy released in each reaction using the mass data. Which reaction will produce more energy per event? Based on the binding energy per nucleon curve, explain why both reactions can release energy despite one reaction combining nuclei and the other splitting them. The Kepler engine must be maintenance-free for a century and must not produce any waste requiring human handling. Use your physics knowledge, evaluate which process, fusion or microfission, is more suitable for the station, regardless of the total energy per event. So pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, the fusion mass defect is equal to the change in mass, so it's 0.00531 U. So the energy released, we multiply by 931.5 is 5.06 MeV. We then do the same for fission, and we get the energy released to be 61.48 MeV. So in this instance, fission will release more energy per event. Secondly, fission will join light nuclei to form products with a higher binding energy per nucleon. Fission splits heavy nuclei into more tightly bound fragments. Both result in a net increase in binding energy, so energy is released. Now you should pick fusion. Fission produces radioactive waste and requires waste handling systems. Fusion produces no long-lived radioactive byproducts and is better for autonomous operation. The fusion fuel is also lighter and can be potentially harvested from the gas giant that it is orbiting around. An ancient alien probe is discovered beneath the oceans of Europa. At its core is a power unit dubbed the Poseidon core, which appears to derive its energy from a chain of fusion and fission reactions. Physicists on Earth decode a fragment of its operating record. Now use the binding energy per nucleon data to determine whether the stated energy release of 7.65 MeV during the formation of carbon-12 is consistent with the physics of fusion. The second stage of the Poseidon core supposedly causes carbon-12 to split into lithium-6 and helium-6, using the binding energy per nucleon values to determine if this reaction would release or require energy. Finally, Poseidon's design appears to use an unstable isotope for controlled energy modulation, suggests a reason why the system may deliberately include a nucleus with a low binding energy per nucleon, and evaluate the risks and benefits of doing so in a self-contained, unmanned power core. So pause the video now, and then unpause the video when you want to go through your answer. In our first one, the total binding energy is 3 times by 4 helium, so it's 21.21. The total binding energy of the carbon-12 is going to be 92.16, there's 12 there, so therefore the difference in total binding energy is 70.95 MeV. So the claimed output is not consistent with this, it actually underestimates the actual energy gain found. Secondly, the total binding energy, as we just said, is going to be 92.16 for the carbon. The total binding energy of the lithium and the helium, when we work it through, is 61.26 MeV. So therefore this tells us the binding energy has decreased by 30.9 MeV. So therefore if we've lost it and it's decreased, energy is required, not released. So it's not a spontaneous reaction, we would have to trigger it. Finally, low binding nuclei are more likely to undergo decay or induce fission, so it may serve as energy control triggers. It allows clear tuning of output or emergency shutdowns via controlled instability. The risks are a potentially uncontrolled chain reaction or structural instability over time, but the benefits enable a fail-safe assembly must be weighed against the risk of radiation leakage or runaway chain reaction. The next question says, a nuclear power station uses a thermonuclear reactor to generate electricity. The reactor uses uranium-235 fuel and is designed to operate using thermal neutrons. During a routine inspection, engineers observe a slight increase in the core temperature and a higher than expected neutron flux. Explain how the moderator and control rods work together to maintain a steady rate of fission in the reactor, including your answer the physical processes involved and the importance of thermal neutrons. The engineers consider replacing the graphite moderator with a denser material to improve neutron slowing. Evaluate this decision. Then a student claims that increasing the mass of uranium fuel in the reactor will always increase the power output. Critically assess this statement considering the concept of critical mass and reactor safety. So pause the video now and then unpause the video when you want to go through your answer. Right, the moderator slows down fast neutrons via elastic collisions. Thermal neutrons are more likely to induce fission in uranium-235, so the control rods will absorb the excess neutrons to prevent a runaway chain reaction. Now, good moderators must slow the neutrons effectively without absorbing them. The denser materials may cause more inelastic collisions or could absorb neutrons. So graphite and heavy water are effective due to their low neutron absorption cross-section. So replacing graphite with a denser material could actually reduce reactor efficiency. Finally, increasing the fuel mass increases fission probability only up to the critical mass. Beyond the critical mass, the uncontrolled chain reactions may occur, so the reactor design includes control systems to manage our amount of neutrons and our neutron flux. Now, the student's claim ignores safety limits and reactor design constraints. A nuclear reactor uses uranium-235 fuel and operates using thermal neutrons. The reactor is monitored using sensors that measure neutron flux and core temperature. The table below shows data collected during a 10-minute period after a partial failure of the control rod insertion system. Describe the relationship between the neutron flux and the core temperatures shown in the data. Explain how this relates to the concept of a chain reaction in a nuclear reactor. The engineers suspect that the control rods are not functioning correctly. Use the data to evaluate this suspicion and explain the role of control rods in maintaining reactor safety. A student claims that increasing the coolant flow rate will reduce the neutron flux. Assess this claim using your understanding of the roles of the coolant and neutron moderation in the thermal reactor. So pause the video now and then unpause the video when you want to go through your answer. Right, in our first one, the neutron flux and the core temperature, as you can see from the data, both increase over time. So this is suggesting an accelerated chain reaction. More fissions release more energy, increasing the temperature. And it's a positive feedback loop if it's not controlled with control rods, as shown in the data. The control rods absorb excess neutrons to limit the chain reaction. The data shows increasing neutron flux, suggesting insufficient absorption of the neutrons. So the temperature rise supports the idea of uncontrolled fission. So the conclusion must be that the control rod failure is a plausible explanation for this. The coolant removes heat, but it doesn't directly affect how many neutrons are present. The neutron flux depends on the moderation and the control rods, not the temperature alone. Increasing the coolant flow may reduce the temperature, but not how many neutrons are present. So the student's claim is incorrect. The coolant will affect the thermal management of the reactor, not how many neutrons are present. A nuclear energy company is developing a new type of thermal nuclear reactor. They are comparing data for four materials under consideration as moderators or coolants. The aim is to maximize neutron moderation efficiency while minimizing safety risks and material degradation under reactor conditions. The table below shows the properties of four candidate materials. Using the data, explain which two materials are most suitable to act as a moderator and a coolant. Justify your choices using multiple data points from the table. Explain how the process of neutron moderation enables a sustained chain reaction to occur in a thermal reactor. A student suggests replacing heavy water with liquid sodium to save cost. Evaluate this suggestion using both physics and safety considerations. So pause the video now, and then unpause the video when you want to go through your answer. Right, the moderator should have a low atomic mass to maximise the elastic energy transfer, so this indicates that helium or graphite are the best. The moderator should have a low neutron absorption cross-section area to avoid the loss of neutrons. Helium and heavy water are the best for this. Now the coolant needs a high specific heat capacity and a high melting point. Graphite and helium score well on the melting point, and helium and heavy water have a high specific heat capacity. The liquid sodium has a high neutron absorption, so it can't be suitable as a moderator. So our final justified selection should be helium as a moderator due to the low mass and very low neutron capture, and either graphite or heavy water as the coolant. The fast neutrons that are produced in fission must be slowed down to become thermal neutrons. Moderation occurs via elastic collisions with these light nuclei. The thermal neutrons are more likely to induce fission in uranium-235, enabling that sustained chain reaction. If too many neutrons are absorbed or escaped, the mass will drop below the critical mass and the chain reaction stops. Finally, liquid sodium has a high neutron absorption, which would reduce fission rate and increase reactor instability. Sodium is highly reactive and flammable, posing greater safety risks than heavy water. Although it might be cheaper, the risk and performance trade-offs made it an unsuitable substitution. A nuclear facility generates radioactive waste from its reactors. The waste includes isotopes that vary in half-life, radiation type, and penetration depth, which affects the design of containment and disposal strategies. The table below shows data for four common waste isotopes. Using the data, identify which two isotopes pose the greatest long-term hazard to human health and the environment. Justify your answer. Explain why alpha radiation, despite being the least penetrating, requires stringent containment protocols during storage and handling. The waste facility is considering above ground storage for all four isotopes. Critically evaluate this decision using the data and your understanding of radioactive decay, including environmental and safety factors. So pause the video now, and then unpause the video when you want to go through your answer. Right, in this one, plutonium-239 has a very long half-life, so it would remain hazardous for millennia. So despite alpha radiation, if radiotoxicity if inhaled or ingested is extremely high. Now cesium-137 is also hazardous due to gamma emission and a long half-life. So therefore, the ones that have the greatest risk are going to be the plutonium-239 and the cesium-137. Secondly, alpha particles have a low penetration, but they have an extremely high ionizing power. So if inhaled or ingested, it can cause severe localized damage to tissue and DNA, possibly leading to cancer or cell death. So strict containments prevent aerosol contamination and an inhalation risk for people. Finally, above ground is suitable for short-lived isotopes such as iodine-131 as it decays quickly, but long-lived isotopes such as plutonium need secure, deep geological storage to prevent leakage. Also, gamma emitters such as cesium will require heavy shielding, which increases the infrastructure cost and the complexity of the project. Now, environmental risks could include things like natural disasters, access by terrorists, or container degradation over time, which we've got to consider. So, that brings an end to our revision session today. If we've been successful and we've learned in today's revision session, we should be able to answer A-level physics exam style questions, assess your understanding on A-level physics, and then finally understand what topics we need to improve upon for A-level physics. So thank you so much for watching this revision session on paper 2 for AQA A-level physics, looking at the concept of nuclear physics and in particular nuclear processes. Thank you so much, and as always, have a lovely day.